unit, and so we're going to put it all together today. And this lesson is a little bit longer, so it'll count as both of their activities for this week. So last week in lab, we did a lab where you guys played with a skater, and you parked her up here at 6 meters, and she just zooms down the hill and then goes up the other side. And one of the things we did was we made sure there was no friction. So we put the friction at none over here. So she's not losing any energy to friction. And what that means is that she keeps coming back to the same height she starts at, 6 meters. And so what we did was we stopped her at various places and we measured her speed and her height, and we found her kinetic energy and her potential energy. And what we got when we did that looks something like this in our lab. Okay, so at a whole bunch of different heights. So at 6 meters high, we calculate her potential energy. And remember, potential energy we calculate using m times g times h. We measured her velocity using the speedometer, which was right here. We calculate her kinetic energy, and remember her kinetic energy is 1/2 her mass times her velocity squared. So right there it tells us her kinetic energy. So if you take 1/2 her mass, which was 60, so 1/2 of 60 is 30, times her velocity squared. Well, here her velocity was 0, so she's not moving, so she has no kinetic energy. And then we found the total energy. We added up the potential and the kinetic, and we got the total energy. So the skater starts off with 3,600 joules of total energy. And then here's what happened. When she went down the hill, she was at 5 meters high now. Her potential energy got smaller, but she started moving, so her kinetic energy got bigger. And so what our graph shows us is the blue line shows us that as she goes down the hill, her potential energy gets smaller. And the red line shows us her kinetic energy. Her kinetic energy got bigger and bigger and bigger. But here's the cool thing. When you added the potential and the kinetic together, you always got the same thing. So the total energy stayed the same. And that's the big idea for the unit. The total energy of a system always stays the same. All right, so if you take the kinetic energy plus the potential energy and you add them up, you always get 3,600. So as she loses potential energy, she was gaining kinetic energy. And the total energy stays the same. So this is what we have right here. This is the big idea. The total energy is the kinetic energy plus the potential. So let me show you on Skater Park a little graph that kind of helps. So right up here, if I click this button, you can go try this if you want. What it shows us is the total energy here on this graph right here. This green graph shows us her kinetic energy, and the blue graph shows us her potential energy. So you can see that her kinetic and potential energy keep going up and down. When she's at the tippy top, she's not moving, her kinetic is 0. Right now at the bottom, she's moving really fast, so she has lots of kinetic energy, but she doesn't have any potential energy. And then as she starts to go up the hill, her potential energy is getting bigger and bigger, and her kinetic energy is getting smaller and smaller. And when she gets to the tippy top, she has no kinetic energy because she's not moving, but it's all potential. But if you notice her total energy, the total energy she has, that always stays the same. Okay? And we're going to use that principle to help us solve some problems. All right? So the idea is whatever energy she starts with, that's the total energy she has all the time. As she loses one kind of energy, she gains the other. But if you take the kinetic plus the potential, you'll always get the same thing. Okay, that's called conservation of energy. Now, in the real world, there's a little bit of friction. So if I add in some friction here, you'll notice that her kinetic energy and her potential energy keep going back and forth. But as she keeps moving, her thermal energy, which is the heat produced as the wheels turn and things, that is actually growing. So her kinetic energy is getting less and less. She's not going as high every time, but her total energy still stays the same. So even if we used a real world problem, the total energy would still stay the same. It's just some of it's going into heat, which we can't account for right now. So we're ignoring friction in this lab. Okay? So what I'm going to do is I'm going to solve an example problem for you. So work through this example with me. I know it's not the most exciting thing to do is to watch a video of somebody else solving a problem. But then when I'm done, you're going to solve an almost identical problem with different numbers for your assignment, for your homework. So it'll really help if you can kind of watch the problem I'm going to solve next. Okay? All right. So here we go.